In this unit, we will introduce you to the world of machine learning with ROCm. Machine learning is a branch of artificial intelligence that has revolutionized the way we tackle complex problems and make data-driven decisions. Machine learning workloads usually requires large-scale data processing and highly parallel execution, therefore are suitable for GPU execution. Therefore, ROCm seamlessly support popular machine learning frameworks such as PyTorch and TensorFlow. These frameworks are widely adopted in the machine learning community, and with ROCm support, we can leverage their capabilities while maximizing the performance of AMD GPUs. This combination unlocks a whole new level of computational performance, enabling us to tackle large-scale and computationally intensive tasks with ease. Now we will introduce you to the powerful combination of PyTorch and ROCm, a platform for accelerating machine learning applications on both CPUs and GPUs. PyTorch is developed by Facebook Research and has emerged as a popular library for deep learning, providing programmers with intuitive APIs to define and train neural networks. What makes PyTorch on ROCm truly remarkable is its ability to seamlessly leverage the development skills of programmers who have previously worked with torch.CUDA interfaces designed for CUDA-based systems. The backend of PyTorch on ROCm takes care of invoking the appropriate ROCm libraries, ensuring different execution on AMD GPUs. Let's take a common function that we often encounter in many machine learning applications such as torch.cuda.is_available function, which is used to check the availability of a GPU. The great news is that with PyTorch on ROCm, Python programmers can seamlessly utilize this function without the need for any modifications. It ensures a smooth transition and allows developers to leverage familiar functionalities without any hassle. The seamless interoperability between AMD and NVIDIA systems brings out a remarkable advantage by significantly reducing the effort needed for migration and eliminating the requirement for extensive code rewrites. This means that developers can smoothly transition their code between these systems without facing the burden of extensive modifications or rewriting their existing code base. It simplifies the process and enables a more efficient and streamlined workflow for developers working with diverse hardware configurations. By embracing PyTorch on ROCm, developers can unlock the advantages of AMD GPUs while utilizing the familiar PyTorch APIs they are accustomed to. Whether it's defining complex neural network architectures, optimizing models, or efficiently loading and preprocessing data, PyTorch on ROCm empowers developers to leverage their existing skills and achieve high performance across a range of platforms. Before we can utilize the power of PyTorch on ROCm, we need to begin by installing the PyTorch framework. Next, we will see how to install the PyTorch framework. When it comes to installing PyTorch, we will come across various methods, but we will share the recommended approach, which is using the Docker image with pre-installed PyTorch. This method saves you time by eliminating the need for manual compilation, allowing you to quickly get started with PyTorch. Additionally, the Docker container ensures consistency as it has been thoroughly tested and optimized, eliminating any potential installation issues that could hinder your workflow. We can pull the latest public PyTorch Docker image by executing the command docker pull rocm/pytorch:\latest. This command will fetch the most up-to-date version of the PyTorch Docker image from the public repository. Now that you have obtained the PyTorch Docker image, you are ready to use PyTorch and leverage its powerful machine learning capabilities. Let's move on to the next step to make the most out of the Docker image. Now we will launch a Docker container using the downloaded PyTorch image. To initiate the Docker container, we need to execute the command from the slide. This command sets in motion a Docker container equipped with essential configurations to optimize your PyTorch experience. It grants access to system-level resources such as kernel features, security permissions, video devices, and shared memory allocation. By leveraging this Docker container, you gain a well-prepared environment to explore PyTorch's capabilities, experiment with machine learning models, and execute code effortlessly. It encapsulates the required dependencies and configurations, ensuring a smooth and consistent experience across different systems. Now that we have gone through the installation process, it's important to ensure that PyTorch is installed correctly and functioning properly. In this section, we will walk through the steps to test our PyTorch installation. The first step is to ensure that PyTorch is installed and accessible on your system. We can do this by importing the torch package in Python. Running this simple command from the slide will help verify if PyTorch is properly installed. If it is, you will see a success output indicating that PyTorch is ready to be used. Otherwise, you will see a failure output indicating that further troubleshooting might be needed. Next, we will test if the GPU is accessible from PyTorch. PyTorch provides a mechanism called torch.cuda to access the GPU. By invoking torch.cuda.is_available function, we can determine if the GPU is available and ready for use with PyTorch. If a GPU is available, the output will be true, indicating that PyTorch can leverage the GPU for accelerated computations. On the other hand, if a GPU is not available, the output will be false, suggesting that PyTorch will rely on CPU computations. To thoroughly validate our PyTorch installation, we will run a set of unit tests. These tests cover various aspects of PyTorch functionality and ensure that everything is working as expected. By executing the specific command from the slide, we can run these tests and obtain comprehensive validation. For a more detailed examination of specific areas with PyTorch, you can run individual unit tests. This allows you to focus on particular functionalities or modules. By specifying the tests that you want to run, you can gain deeper insights into PyTorch's capabilities. The test _nn.py in the command can be replaced with any other test set. Now let's take a look at a case study that showcases the use of machine learning with ROCm. We will explore the renowned Inception v3 model, which is widely used for image processing tasks. To make the deep neural network configuration easier, we use Torch Vision, a handy library that gives us access to pre-built models and datasets. It even comes with pre-trained weights. In this case study, we won't be training the model from scratch. Instead, we will be putting its pre-trained parameters to the test with an image classification task. We will see just how well the Inception v3 model performs on new and unseen images. Let's explore the image classification with Inception v3 code together and understand how the evaluation of the Inception v3 model is performed. At first, we will import the necessary libraries into our Python script. Import torch imports the PyTorch library in our Python script. PyTorch is a popular open-source deep learning framework that provides a wide range of tools and functionalities for building and training neural networks. And import Torch Vision imports the Torch Vision library, which is a PyTorch package specially designed for computer vision tasks. It provides convenient access to popular datasets, model architectures, and image transformations, making it easier to work with computer vision tasks in PyTorch. After importing the necessary libraries, we proceed to load the pre-trained Inception v3 model using the torch.hub.load function. This function allows us to conveniently access pre-trained models from the PyTorch/Vision repository. In this case, we specify the repository, the model name, and set pre-trained as true to load the pre-trained weights of the model. By calling model.eval function, we switch the model into evaluation mode. This ensures that the model behaves correctly during the evaluation phase by disabling any layers of operations that are only needed during training. It's important to note that this step is necessary when working with pre-trained models as they may have different behaviors during training and evaluation. Overall, these two lines of code load the pre-trained Inception v3 model and prepare it for evaluation by switching it to evaluation mode. The next part of the code deals with downloading an image that we will use for testing the Inception v3 model. We start by defining a URL and a file name. In this case, the URL points to an image of a dog hosted on GitHub, and we assign the file name as dog.jpg to save the downloaded image. Next, we use a try except block to handle the download process. The code attempts to download the image using the urllib module in Python, especially the URL opener class, by calling the retrieve method on an instance of this class. This method retrieves the file at the specified URL and saves it with the given file name. In case the above method fails, an exception is raised indicating that the Python version may be using the urllib module in Python, specifically the request submodule, by invoking url.retrieve function with a specified URL and file name instead. This alternative method achieves the same result of downloading the image and saving it with the specified file name. Overall, these lines of code handle the download of an image file from a specified URL and save it with the provided file name, ensuring that we have an image to work with for testing the Inception v3 model. Once the image is downloaded and saved as dog.jpg, we can proceed to open and process the image using the Python image library and the Torch Vision library. First, we import the necessary modules, image from PIL and transforms from Torch Vision. Next, we use the image.open function from PIL to open the downloaded image. The image.open function reads the image file specified by the filename variable and returns an instance of the image class representing the opened image. The assigning the returned image instance to the input_image variable, we can access and manipulate the image for further processing and evaluation using the Inception v3 model. In summary, these lines of code import the required modules, open the downloaded image using PIL, and store it in the input_image variable for subsequent processing. After opening the image using PIL, we need to perform a series of image transformations to preprocess it before passing it to the Inception v3 model for evaluation. To accomplish this, we utilize the powerful transforms.compose function provided by the Torch Vision library. To begin, we define a preprocess variable and assign it a transforms.compose object. This object serves as a container for a sequence of image transformations that will be sequentially applied to the image. The first transformation we apply is transforms.resize, which resizes the image to a square shape with dimensions 299 by 299 pixels. This specific size is required as the input dimension for the Inception v3 model. Next, we apply transforms.centerCrop, which performs a center crop on the image. By extracting a square region of size 299 by 299 pixels from the center of the image, we maintain the aspect ratio and focus on the main subject of the image. Following that, we apply transforms.toTensor to convert the image into a PyTorch tensor. PyTorch tensors are fundamental data structures used for representing and manipulating data in PyTorch. This transformation not only converts the image into a tensor format but also normalizes the pixel values. Lastly, we apply transforms.normalize function, which performs mean and standard deviation normalization on the tensor image. Normalizing the image contributes to improved model performance and convergence during training. By applying these transformations in a sequential manner, we ensure that the input image is properly preprocessed and ready to be fed into the Inception v3 model for evaluation. After applying the image transformations, we obtain the preprocessed image tensor using the preprocessed transformation pipeline. The input_tensor variable now holds the preprocessed image tensor. Next, we prepared the input tensor for the model evaluation by creating an input batch. In this case, we add a batch dimension to the input tensor using the unsqueeze method. This is because the Inception v3 expects input data in a batch format even if we are evaluating a single image. To utilize the GPU for faster computation, we check if a GPU device is available by using the torch.cuda.is_available function. If a GPU is available, we move both the input batch and the model to the GPU device using the toCUDA function. This enables us to perform computations on the GPU, which can significantly accelerate the evaluation process, especially for large models and datasets. By transferring the input batch and the model to the GPU, we ensure that the model evaluation takes advantage of the available hardware acceleration, if applicable. This can lead to faster inference time and improved performance when working with deep learning models. To ensure that no gradients are computed during the evaluation process, we use the torch.no_grad context manager. This temporarily disables gradient computation, which reduces memory usage and speeds up the evaluation. Within this context, we pass the input batch to the model function. The output variable now holds the output of the model for the given input batch. Next, we apply the softmax function to the output tensor using torch.nn.functional.softmax function. This converts the raw output values into probabilities where each value represents the likelihood of the input image belonging to a specific class. The output tensor contains the raw output values produced by the model, which represents the model's confidence scores for each class. Finally, we print the probabilities tensor, which now contains the class probabilities calculated by the softmax function. This provides a more interpretable representation of the model's predictions, showing the probability of the input image belonging to each class in the dataset. Then we perform post-processing of the predicted probabilities to obtain the top 5 predicted classes and their corresponding probabilities. First, we open the file imagenet_classes.txt in read mode. This file contains a list of categories or class labels corresponding to the ImageNet dataset. Moving forward, we proceed to read the lines from the file and store them as categories in a list. Later, we utilize a function to extract the top 5 probabilities and their corresponding indices from the tensor of probabilities. These probabilities represent the likelihood of certain classes. To present the results in a more understandable format, we iterate over the top 5 probabilities. During each iteration, we retrieve the category label associated with the predicted class index and the probability value. By printing this information, we can obtain a human-readable summary of the model's predictions, showcasing the top predicted classes and their probabilities. Now we need to run the Python script within a Docker container. To execute a Python script within a Docker container, we can utilize the provided command in the slide. This command launches a Docker container based on the latest ROCm/PyTorch image, incorporating a range of configurations and options. Notably, we employ the mount flag to establish a connection between a directory on the host machine and the Docker container. By specifying type as bind, we indicate the utilization of a bind mount, which facilitates the seamless integration of a host machine directory into the container's file system. This allows for easy data sharing and interaction between the two environments. The source parameter designates the path to the desired host machine directory to be mounted, while the target parameter specifies the corresponding location within the container where the directory will be accessible. Upon executing this command, you will be seamlessly transitioned into the interactive environment of the Docker container. This means that the command will initiate the container and provide you with a prompt, allowing you to directly interact with the container's command line interface. From here, you can execute further commands, run Python scripts, and perform various operations within the isolated container environment. Once we enter the interactive mode of the Docker container, the next step is to acquire the essential text file required for classifying images in the image classification example. This text file is crucial for mapping the output probabilities of the pre-trained Inception v3 model to their corresponding class labels. The command displayed on the slide, along with the provided link from a GitHub repository, will enable us to download the necessary text file. Next, we can proceed to execute the Python script by using the command python3filename.py within the Docker container. This command triggers the execution of the specified Python file and generates the desired output. The execution of the Python file will generate a tensor as the output, which will contain the probabilities for each class in the model's output. The dimensions of the tensor will vary based on the number of classes involved in the classification task. Each element within the tensor corresponds to the probability of its respective class. The output also provides the top 5 predicted categories for the input image, along with their corresponding probabilities. This information offers valuable insights into the model's predictions for the given image. Each category is imprinted alongside its probability, allowing us to understand the model's confidence levels and the likelihood of each predicted category. According to the model, the input image contains a Samoyed dog with a probability of 0.8238, which is the highest probability. In conclusion, PyTorch on ROCm offers seamless interoperability between AMD and NVIDIA systems, enabling developers to harness the power of AMD GPUs without the need for extensive code modifications. By combining the ease of use and flexibility of PyTorch with the computational capabilities of ROCm, we open up new possibilities for accelerating machine learning applications and driving breakthroughs in the field. Now we will do a performance analysis to compare the execution times on the GPU and CPU for an image classification task utilizing the pre-trained Inception v3 model. For this analysis, we will use the profiler provided by PyTorch. The profiler allows us to profile the execution of a PyTorch script and gather detailed information about the execution time and memory usage of different operations within the script. By profiling the code, we can gain insights into the performance characteristics of our implementation and identify potential bottlenecks in terms of execution time and memory consumption. We are using the same code as before for an example in the performance analysis task by bringing some small changes to it. We wrap a piece of code by the PyTorch profiler, keeping the rest of the code unchanged. As we can see from the slide, by using the combination of torch.no_grad function and the torch.autograd.profiler.profile function, the code ensures that gradient calculations are disabled and profiling information is collected during the execution of the model with the given input batch. This allows us to analyze the time taken by different operations within the model and understand how much time is spent on GPU computations and CPU computations, which we will be seeing in a while. After wrapping the code with the profiler provided by PyTorch, we need to add the print function to print the profiling information at the end of the execution of the whole Python script. By executing the print function, we will see the profiling information in the form of a table where the operations are listed along with their respective execution times on the CPU and GPU. The table is sorted based on the CUDA_time_total column, allowing us to identify operations that consume the most GPU time during execution. After executing the Python script, we get the regular image classification output that we have discussed before along with the profiling table. The table provides a breakdown of different operations and their corresponding metrics. Let's go over some of the columns. The name column shows the name of the operations being profiled. Self-CPU percentage columns represents the percentage of CPU time attributed to the operation itself. Self-CPU column shows the total CPU time spent in the operation excluding any sub-operations. CPU total percentage indicates the percentage of CPU time attributed to the operation and its sub-operations. The CPU total column represents the total CPU time spent in the operation and its sub-operations. Self-CUDA column represents the percentage of GPU time attributed to the operation itself. Self-CUDA percentage column represents the percentage of GPU time attributed to the operation itself. And the CUDA total column shows the total GPU time spent in the operation and its sub-operation. In this slide, we have included a partial snapshot of the table due to the limited space available. The table provides detailed information, but due to constraints, we are presenting only a portion of it. Upon examining the specific output, we can observe the distribution of time among different operations during GPU execution. One notable example is the convolution operation, represented by both @:convolution and @:convolution, which refer to different implementation details or variants of the same operation. These operations exhibit similar profiles, accounting for nearly the entire CPU time at 99.61% and also consuming a significant amount of CUDA time. The number of calls for both operations is 94, indicating repeated invocations during the model's execution. One thing to note, the CPU total time for the convolution operation is considerably higher compared to the CUDA total time. Specifically, the CPU total time is 80.124 seconds, while the CUDA total time is only 7.144 milliseconds. Remember, the CUDA time represents the GPU execution time. By examining other operations and drawing similar conclusions, we can utilize the profiler output to identify potential performance bottlenecks. This information helps us target the operations with the highest time consumption on both the CPU and GPU, enabling us to optimize our code effectively. Based on the profiling results, it becomes evident that the convolution operation is the most time-consuming in terms of both CPU and GPU. And GPU plays an important role in reducing the time for executing the convolution layer. Its frequent occurrence throughout the model's execution emphasizes its significance in overall performance. After analyzing the profiling table, we can observe the GPU execution time and the CPU execution time. The self-CUDA time total, which represents the GPU execution time, is measured to be 4.380 milliseconds. On the other hand, the self-CPU time total, indicating the CPU execution time, is measured to be 80.347 seconds. By comparing these values, we can conclude that the GPU execution time is notably lower than the CPU execution time in this specific scenario. This comparison highlights the efficiency of GPU parallel processing in performing certain operations compared to CPU execution. The GPU, with its specialized architecture designed for parallel computations, can significantly reduce the execution time for certain tasks. In this case, utilizing the GPU has resulted in a considerable reduction in execution time compared to relying solely on the CPU. Such findings show the advantage of leveraging GPU acceleration for computationally intensive tasks, as it can offer substantial performance gains and accelerate the overall execution of the code. So far, we have introduced how to use PyTorch on ROCm platform. Let's summarize. In this section, we focused on the efficiency of machine learning on ROCm using the PyTorch framework. We started by learning how to easily install PyTorch using the simplest and most convenient methods. We also learned how to perform a test to make sure PyTorch is installed correctly. Then we applied the pre-trained Inception v3 model to an image classification task. By harnessing the power of the GPU, we experienced significant improvements in efficiency thanks to GPU acceleration in deep learning models. To thoroughly evaluate and compare performance, we conducted a comprehensive performance analysis using a specialized tool provided by PyTorch. These analyses involved measuring execution times on both the GPU and CPU, providing valuable insights into the crucial role of the GPU in reducing overall execution time. By gaining hands-on experience with PyTorch and ROCm and exploring the efficiency enhancements brought by GPU utilization, we now have a comprehensive understanding of the benefits and capabilities of machine learning on ROCm.